The angle bisector property. Welcome, everyone. Before we dive into today's new concept, let's take a moment to reflect on what we have already mastered. In our previous lesson, we established Theorem 10.2, which is a fundamental building block for what we are about to discuss. As a quick refresher, that theorem provides us with the proof that the lengths of two tangents drawn from the same external point to a circle are exactly equal to each other. Now, today, we're going to look at a very important and direct consequence of that theorem, which we call a corollary. This is known as the angle bisector property. Essentially, this property is going to show us a specific angular relationship between the center of the circle and the two tangents that meet at that external point. By the end of this session, you'll see how the geometry of the tangents and the center of the circle are perfectly linked. Understanding the concept. Imagine we have a circle with its center at point O now. Let's pick a point, P, that lies outside of this circle. From this external point P, we draw two tangent lines that just touch the edge of the circle. We'll call these points of contact Q and R. Here is the core of the concept. If you draw a straight line segment from that external point P directly to the center of the circle, point O, you've just created an angle bisector. To be more specific, this line segment, OP, cuts the angle formed at the vertex P, which is angle QPR, into two perfectly equal halves. In mathematical terms, this means that the angle OPQ is exactly equal to the angle OPR. What this tells us, and what is vital to remember for the upcoming proofs, is that the center of the circle, O, will always lie precisely on the line that bisects the angle formed by those two tangents. As we will see in the next slide, we can actually prove this using triangle congruence. Now that we've recalled Theorem 10.2 and established that the lengths of the tangents are equal, let's move on to slide 2 to see what this actually looks like in practice. Step-by-step logical derivation. Now that we have a conceptual idea of what the angle bisector property looks like, let's move into the why. You might be wondering, how do we actually prove that this line really does bisect the angle? To do this, we are going to use a logical derivation, breaking it down into 3 clear steps using the concept of congruent triangles. Step 1. First, let's identify the triangles we are working with. If you look at the diagram, we can create two triangles by drawing lines from the center, point O, to our external point P, and then connecting that to our points of contact, Q and R. This gives us two triangles to compare: triangle OQP and triangle ORP. Step 2. Next, we need to establish congruence. To prove two triangles are identical, we need to show their sides are equal. We can pull this evidence from what we learned in the previous section, Theorem 10.2. First, we know that OQ equals OR because they are both radii of the same circle. Second, we know that PQ equals PR because we already established that tangents from an external point are equal in length. And finally, we have the side OP, which is common to both triangles. Since all three sides are equal, we can use the SSS, or side-side-side, congruence criterion to state that triangle OQP is congruent to triangle ORP. Step 3. Now, here is the most important part. Because we have proven these triangles are congruent, we can apply a rule called CPCT, which stands for corresponding parts of congruent triangles. This rule tells us that if the triangles are identical, then their corresponding angles must also be equal. Therefore, the angle OPQ must be equal to the angle OPR. To conclude our derivation, because the line segment OP divides the larger angle, angle QPR, into two perfectly equal parts, we have mathematically proven that the line OP is indeed the angle bisector of angle QPR. Now that we've seen the mathematical proof, let's look at how this principle actually applies to a real-world scenario, like designing a park. Real-world example, the circular fountain design. Now that we have mathematically proven why these triangles are congruent and why the angles must be equal, let's step away from the abstract geometry for a moment and see how this property actually works in a real-world scenario. Imagine you are a landscape architect tasked with designing a beautiful circular fountain in a public park. To set the scene, picture two straight walking paths that both begin at a single entrance gate, which we will label as point P. These paths run perfectly tangent to the edge of the circular fountain, touching the circle at two specific points, which we'll call point Q and point R now. Your goal is to place a decorative lamp post exactly at the center of this fountain, which we will denote as point O. To achieve this precision, you can follow a simple three-step process based on the property we just learned. In step 1, you first identify the angle. You would start by measuring the angle QPR, which is the angle formed by the two walking paths right at the entrance gate. In step 2, you perform the bisection. Using the property of the angle bisector, you simply calculate half of that angle, which is 1/2 of angle QPR. Finally, in step 3, you determine your direction. By walking along a path that perfectly bisects angle QPR, you are mathematically guaranteed to be walking in a straight line that leads you directly to the center, point O, of the fountain. It is a perfect practical application of the theorem we just discussed. Now, let's wrap up our lesson by summarizing the key takeaways you need to remember for your exams. Key takeaways. First, let's restate the core property itself. Remember, when you have two tangents meeting at an external point, which we've called point P, the line segment that connects that external point directly to the center of the circle, point O, acts as an angle bisector. This means it perfectly splits the angle formed by those two tangents into two equal halves. To put this into a mathematical expression that you can use in your proofs, we write angle O, P, Q equals angle O, P, R. This notation is simply our way of stating that the two resulting angles are identical. In terms of its geometric significance, it is important to realize that the center of the circle, point O, is not just randomly placed. It will always lie precisely on the angle bisector of the angle formed by the tangents. This is a powerful tool when you are solving geometry problems involving circles and lines. Finally, I want you to remember the dependency of this property. It is crucial to understand that this property doesn't just exist in isolation. It is a direct consequence of the congruence of triangle O, Q, P, and triangle O, R, P, as we saw in our logical derivation earlier. Because these two triangles are congruent, all their corresponding parts must be equal. All right, class, we have reached the end of our lesson, so let's take a moment to consolidate everything we have learned today. On this slide, we have our key takeaways to help you summarize the angle bisector property. Keep these points in mind as we move into our next slide, where I will highlight some common pitfalls to watch out for during your exams. Common mistakes to avoid. First, be very careful not to confuse the different angles involved in our diagram. It is common to mix up the angle at the external point, which we call angle QPR, with the angle at the center, which is angle QOR. Now, remember what we learned in the previous slides. The line segment OP acts as a bisector for both. It bisects angle QPR, but it also bisects angle QOR when you are solving a problem. Always double-check exactly which angle the question is asking you to find. Second, never assume a line bisects an angle just because it looks perfectly centered on your paper. In geometry, looking correct isn't a valid proof. If you are asked to prove that a line is a bisector, you must always refer back to the logic we used in slide 3. You need to demonstrate that the two triangles, triangle OQP and triangle ORP, are congruent. Without that connection to congruence, your proof is incomplete. Finally, always verify your points of contact. Ensure that points Q and R are truly the points of tangency, where the lines just touch the circle. This property is specific to tangents. If the lines are secants, meaning they pass through the circle and cross it at 2 points, this property simply does not apply. Always check the definition of the lines before you start your calculations. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even when you understand the logic behind the angle bisector property, it is very easy to make small errors during exams. Let's look at 3 specific mistakes to avoid. Keep these points in mind, and you'll be well on your way to mastering circle theorems.